Okay, let's talk about the ratio test. It's one of my favorites, very powerful test. Start with an example. Here is a series. Let's look at the sum from 1 to infinity of n over 2 to the n. So if you start plugging in numbers, that's 1 over 2 to the first, 1/2, plus 2 over 2 squared is 2 over 4, also a half. 3 over 2 cubed, 8, plus 4 over 16, plus 5 over 32, plus 6 over 64, and so on. We want to know, does this converge or not? And it's not obvious what to do here. This isn't a p-test. This isn't geometric. This isn't, the terms are going to 0, so we can't say it diverges immediately. But let's think about what happens, way down the list. So we have the dot, dot, dot. I've got this dot, dot, dot right here. But let's actually go way down the list and keep going. Say we were at like plus 1,000 over 2 to the 1,000th, plus 1,001 over 2 to the 1,001, plus 1,002 over 2 to the 1,002, and so on, right? The thing is, 2 to the 1,000th is like a gigantic number, right? It's like 300 digits or something. It's a big, big number. And 1,000 is not that big comparatively. And so as we actually go from each term to the next, here the numerator is only going up a little bit, but the denominator is doubling, right? That's times 2. This is plus 1. I mean, obviously this is the pattern, but the point is when we get to large numbers, numerator is not changing by much. The denominator is doubling each time. So it's actually kind of like, it's approximately like we're multiplying by a half. So it's not exactly, but it's approximately like we're multiplying by a half. And here, this is approximately like we're multiplying by a half. Oops, times a half. Yeah, so each time, I'm claiming once the numbers get fairly big, you're basically multiplying by a half each time. It's not true for the smaller, the first terms of the series, right? This right here is not multiplying by a half. In fact, it's the same number. And you don't multiply a half by a half here either, and so on. But as the numbers get larger, that's what's happening. So as the numbers get larger, as n gets larger, then we sort of end up in this situation down here. Okay, and so, but basically once you go, and oh, one other thing to say is that, remember, convergence is never in the first million terms of the series. It's always what happens as n goes to infinity. And so as n gets larger and larger, going from one term to the next, we're multiplying by a number closer and closer to 1/2. So as n gets large, I could say it this way if I want to be a little mathematical about it. The n plus first term is very close to the half of the nth term, right? And gets better as n gets larger. This approximation gets better the larger n is. Oops. Gets better the larger n is. And so, in fact, this behaves, in other words, this series is behaving more and more geometric. Siri just thought I said called her because I said the word series. Sorry. Yeah, the series gets more and more geometric. Oh my God, can't write. It's more geometric as n gets large. And in this example here, the r, the thing we multiply by, is 1/2, which is convergent geometric series. right? When the r is between -1 and 1, we know geometric series converge. And so that's actually, the idea here is that basically this looks more and more just like a geometric series with r equals a half. And therefore the argument is the series converges. You can always be a little more rigorous about this, but this is the idea. Okay, so that's kind of an argument we can give for why a series that doesn't satisfy any of the other tests we developed, but it does, we can still show it converges. And the formal way to do this is called the ratio test. So let me just state the ratio test for you. The ratio test says, given a series, I'll just say it equals 1 to infinity. So given such a series, compute the ratio, compute the limit as n goes to infinity of the ratio of the n plus first term divided by the nth term. And let's call that, I think most books call this L, just for limit. I could have used R for ratio, but, and then here's the test. If, and there's 3 cases. If L is less than 1, then the series converges. So that's like the example we just had, right? That's the example, and I'll do it out just a little more formally to show, but going from the n plus first term to the n, going from the n to the n plus first term was like multiplying by a half. So this, in our example, this goes to 1/2, right? The n plus first term is about half the nth term. Okay, so that's the example. We're looking at, if L is greater than 1, then the series diverges. So that's like a geometric series with R greater than 1. Oops, I just wrote the word converges again. And okay, so, and I'll explain this in a second, but if L equals 1, then we actually don't get any information. It doesn't tell us anything. It doesn't predict anything about whether the series converges or diverges. So let me just go back to this. So okay, so this is the ratio test, but then let me state, or let me just show in this example how this would work. So when, so the example we had was the sum of n over 2 to the n, right? So a sub n equals n over 2 to the n. And so we can write down a sub n plus 1, which we really remember what we do is we just replace n with n plus 1 everywhere. And then, oh, I forgot to say something kind of important, which is that, sorry, this really should be an absolute value. It turns out this will actually work for series that aren't positive all the time. So let me just mention this. It's not relevant to this this case, but sometimes you could have something that's like multiplying by negative a half every step or something like that, and that would still work. So there really should be absolute values there. But I'll give an example of that in a moment. Anyway, sorry, back to this example. I wrote down the nth term, I wrote down the n plus first term. So if we look at the ratio, that's really n plus 1 over 2 to the n plus 1 over n over 2 to the n. Remember what we do with ratios of fractions, we flip the bottom one over and multiply by it. So that's like that, right? And how does this, there's some cancellation that goes on here, right? Because we basically have one more 2 on the bottom than on the top. There's 2 to the, we have, if n was 10, we'd have 2 to the 10th on top and 2 to the 11th on the bottom. And so the way this cancels is this cancels and then the n cancels there. And we're just left with 2. So this is n plus 1 over 2n. And we want the limit as n goes to infinity, right? By the way, I guess I should still put the absolute values here. It doesn't matter because everything's positive. And, you know, if I want to take the limit as n goes to infinity, you can just sort of think about the bottoms twice the top, basically. But the way I like to do this a little more rigorously is to multiply the top and bottom by 1 over n. So because we're doing the same thing on the top and bottom, doesn't change what it equals. If we multiply the top, if we sort of FOIL this through, not FOIL, distribute this through, we actually get 1 plus 1 over n. And then the bottom is just 2. And so that's nice now because that's easy to take the limit of. So L here is the limit as n goes to infinity of 1 plus 1 over n all over 2, which is 1 plus 0 all over 2, which is a half. So that's our limit is a half. That's less than 1. So the series converges. So that's how you would apply the convergence test here. Okay, so that's how we use the convergence test. Let me give you an example that diverges. And I also to give you some examples that show you why the L equals 1 gives no info. So if we want something that diverges, let me do the following. This is going to look kind of crazy, but minus 3 to the n, I'm going to use minuses also so that we can see how this works. Over 2 to the n plus 5, something like that. Now, you might be able to guess that this diverges because I'm going to start it at 0, actually, it doesn't matter. But because the top 3 powers of 3 grow faster than powers of 2. So the top actually grows faster than the bottom. But again, let's just write some terms of this out. If we take things to the 0th power, that's 1. So this becomes 1 over 1 plus 5, which is a 6th. Then we get minus 3 over 2 plus 5 is 7, plus 9 over 4 plus 5 is 9, minus 27 over 8 plus 5 is 13, and so on. So you might as well, it's always good to write out a few terms of your series. And let's just say, so this right here is a sub n. So what's a sub n plus 1? Well, again, we just replace n with n plus 1 everywhere. So I just turn the n's to n plus 1s. And then if we do a sub n plus 1 over a sub n, we have minus 3 to the n plus 1 over 2 to the n plus 1 plus 5 times, remember, we're going to flip the bottom over, 2 to the n plus 5 over minus 3 to the n. Okay, and there's some cancellation again we can do. And we have one more minus 3 now on top than on the bottom. And now the plus 5 is getting in the way a little bit. So let me just rewrite what we have. So we got minus 3. By the way, I really should be doing absolute value. So absolute value of everything. So it's absolute value of minus 3. So that's just going to be plus 3. But I'll deal with that in a second. Times 2 to the n plus 5 over 2 to the n plus 1 plus 5. And so that's 3 times 2 to the n plus 5 over 2 to the n plus 1 plus 5. And okay, so what does this happen? Because now as n gets large, the top and bottom of this fraction both go to infinity. But again, this is that trick. It was just like we did above with the 1 over n, where I'm going to multiply the top and bottom by 1 over 2 to the n. Because I can think of multiplying, if I want something that's going to resolve nicely as a limit, right? I'm going to multiply, divide the top and bottom by that 1 over 2 to the n. And then this ends up equaling We still have that 3 there. Now we have 2 to the n over 2 to the n. So that's 1 plus 5 over 2 to the n. Move 2 to the n plus 1 over 2 to the n, which is 2. One more 2 in the n plus 1. Plus 5 over 2 to the n. And that's nice because having the 2 to the n in the bottom, this gets large. So this whole fraction gets small, right, as n gets large. So L, which is the limit as n goes to infinity, a sub n plus 1 over a sub n, well, we just said that's the limit as n goes to infinity, 3 times 1 plus 5 over 2 to the n over 2 plus 5 over 2 to the n. Those 5 over 2 to the n's both go to 0 as n goes to infinity as we take the limit. So we get 3 times 1 plus 0 over 2 plus 0, and that's 3/2, which is greater than 1. So the series diverges. Okay. Okay, so that's an example that both has plus and minuses in it and where you get a ratio bigger than 1. So the series diverges. Okay, like I said, there's one last example. Let me ask why no info when L equals 1. And the short answer to that is that when L equals 1, it really just means the series is not geometric. It's not really behaving geometrically, because the whole idea of the ratio test is that if a series is behaving geometrically, where you're basically multiplying by the same number, maybe not exactly, but approximately as n gets large, then you can just treat it like a geometric series. Here, if L is 1, lots of series could have L equals 1, so lots of non-geometric series. So let's compare our good friendly harmonic series versus the 1 over n squared series, right? This one diverges. This one converges. In this case, an plus 1 over an is 1 over n plus 1 over 1 over n, which is n over n plus 1, which goes to 1 as n goes to infinity, right? Whereas in this case over here, an plus 1 over a sub n is 1 over n plus 1 squared times 1 over n, or divided by 1 over n squared, which is times n squared over 1. So that's n squared over n plus 1 squared, which is n over n plus 1 quantity squared, which still goes to 1 as n goes to infinity. So what we've seen is that we have two different series, one that converges, one that diverges, but where the L is 1 in both cases. So L is 1 here and L is 1 here. But in one case you get divergence, one case you get convergence. So it's not predictive. It doesn't tell apart. Convergence from divergence. So that's why we get no info. So if you try the ratio test and you get 1, that really just kind of means that it wasn't the right test to use. So you should try something else. All right, let's stop there.